Welcome to the presentation. I'm going to present session 4 of module 3 of the subject Water Supply and Treatment Engineering 1846, uh, initiated by Department of Collegiate and Technical Education. Myself, Dr. Prashant, working as a professor and head of the Department of Civil Engineering. We have till now discussed session 1, 2, 3. In this 1, 2, 3, we have discussed about sedimentation. What is sedimentation? Different types of settling tanks. Then what are the theory of sedimentation tank? Then how to design a sedimentation tank. In this session 4, the contents we are going to discuss are sedimentation aided with coagulation, coagulation flocculation, and what exactly is happens in the coagulation process, which is called as theory of coagulation. Then what are the different types of coagulants which are generally used in the treatment of water? See, why? What is this sedimentation aided with coagulation? Sedimentation is used to remove suspended particles where the particle's specific gravity is heavier than water. See, even after removing these particles, sometimes you may find impurities in the water, which might be because of the very small particles. What you can say is colloidal particles, which are present in the water. Even though if you allow the particles to stay for 4 to 5 hours of detention time, these particles are not going to settle, they move up and down. Okay, so in order to remove these types of particles, we have to aid the sedimentation with the help of chemicals called coagulants. So the primary purpose of the coagulation or flocculation process is the removal of turbidity or else removal of very fine particles, very small particles which are not settled in the sedimentation process. It's also fine particles. They cause turbidity in the water. So our aim is to remove the turbidity in the water. So here you can see the figure. When there is a very fine small particles which are present in the water, water looks like brownish as you see in the slide. And if it is removed with the help of coagulants, you find out a clear water without any turbidity. So, in the sedimentation aided with coagulation, we are going to use chemicals to remove very fine particles. See, this is a table which shows the sizes of the particles. Why coagulation is necessary? What is the necessity of coagulation? See, particle with diameter 10 mm, what we call it as pebble. So if you throw the pebble into the water, or if you put the pebble in the water, it's a quiet water, definitely it is going to settle easily with a settling velocity of 0.73 meters per second. If the particle is very small, of the size 1 mm, what we call it as sand particles, it is also going to settle down. Smaller than that, zero point 0.1 mm particle diameter, fine sand, it is also going to settle down. Then 0.001 silt is also going to settle down with a velocity of 8.6 meter per day. But all these particles settles down easily if you give enough time to settle. So under the force of gravity. But in the water, natural water, you may find particles of size 10 micron, that is 0.00001 mm, and 1 nano, that is 0.000001. These particles are called colloids or colloidal particles, large and small colloidal particles. So they may take a lot of time, they are not going to settle so easily. And if we do not remove these particles, definitely it gives turbidity in the water, and water will become not you're not going to get a clear water. So drinking will aesthetically, the aesthetic look of the water comes down. So we have to remove these colloidal particles from the water, which is not possible using the process we have discussed in the module in the session 1 2 3, sedimentation. So our aim in this the session is we have to remove the colloidal particles. How to remove the colloidal particles from the water? So, what are we going to remove using coagulants? Coagulant aided sedimentation required to remove the following impurities. So, this process is going to remove the following impurities. What are that? Very fine particles like miscellaneous fragments of animal and vegetable matter. And we remove plantains. Plantains may be phytoplankton, the very small microscopic plants. It removes finely divided colloidal matter and very small clay particles. And there are some matters which gives color to the water, that is organic coloring matter, partly in solution and partly in colloidal form. And bacteria and viruses also removed to certain extent, and complex mixture of organic matters. These are all removed when we add coagulant in the sedimentation process. What is this coagulation flocculation? In conventional coagulation flocculation sedimentation process, a coagulant means a chemical is added to the source of water to create attraction among the suspended particles. See, these colloidal particles, they move up and down, they never settle. What they do in the coagulation flocculation, they add a chemical. So these chemicals are going to stick to the mud particles as very colloidal particles. So the flocks develops, and the moss develops. When the moss develops, it is going to settle down easily. So the mixture is slowly stirred to induce particles to clump together into flocks. The water is then moved into the quiet sedimentation basis to settle out the solids. That's called coagulation, flocculation. Here I'm showing a slide. Impurities are there. In the first one, small impurities, colloidal impurities, they are not settling. They are moving up and down. They never settles. So even if you allow water for an year, sometimes these colloidal matter may not settle. So what we do, we have to remove it. Otherwise, we do not get good water, drinking water. So we have added coagulant. Coagulants are some chemicals. So these chemicals forms precipitates, and it traps the impurities. See, it is trapping all the impurities. And in the third step, precipitate and trapped impurities, because of the heavy mass, they have settled down. So with the precipitate, even the colloidal impurities which were moving up and down, they have settled down. How do they do coagulation, flocculation? See, generally raw water which has got very fine colloidal particles. Understand? They have been taken to a mixing chamber where it is where the coagulant is added and it is rapidly mixed. Then from the rapid mixing, it is taken to a next chamber which is called a slow mixing. Slowly, water is agitated to form precipitation. And once the precipitation is formed, all the particles are going to be added. Very small particles are going to be added to the coagulant. Then it is taken to a sedimentation tank where it is allowed to stay for some time quiet. And all these coagulant and the particles which are attached to the coagulants, they settle because of its own weight. And clearer water is taken, and whatever the sludge which is developed, which is deposited at the bottom of the tank, is taken outside. This is the general of sedimentation tank aided with coagulation. As I said in the previous class, one flash mixer is there, and next one is the flocculation chamber is there. So mixing takes place very fastly. Then in the flocculation chamber, slowly the water is mixed with the coagulant. Then flocks are formed. It is taken to the sedimentation chamber. It is allowed for some time. The particles are going to settle with the flocks. This is also a figure. You can see suspended matters are in suspension. Small particles. It is going up and down, not settling. Even though we have allowed it we have given enough time. So we have added coagulants. When the coagulants are added, flocculation takes place, and after flocculation, deposition takes place. Deposits and flow moves. This is the figure which gives you information about the flocculation. What happens when a coagulant is added to the water, which sticks the very fine particles which are not removed in the sedimentation tank, normal sedimentation or a plain sedimentation tank? What happens is coagulation and flocculation can be caused by any of the following four theories. One, we have double layer compression. This takes place. Charge neutralization, bridging, and colloid entrapment. So these are the theory of coagulation: double layer compression, charge neutralization, bridging, and colloid entrapment. This is the diffuse double layer compression. Electric double layer is there. If you see the figure, particle is negatively charged particle, and on the surface of this one you have a stern plane, positive charge, and a stripping plane. Okay. So when a coagulant is added, how it is going to have an impact on the negatively charged particle, which does not stick with any other particle and does not settle down also. What it will do? An electric double layer consists of three parts: surface charge, that is charge ions, commonly negative, adsorbed on the particle surface. Then we have a stern layer, counter ions, attracted to the particle surface and closely attached to it by the electrostatic force. Diffuse layer, a film of the dispersion medium adjacent to the particle. Diffuse layer contains free ions with a higher concentration of the counter ions. The ions of the diffuse layer are affected by the electrostatic force of the charged particle. So, when coagulants are added into the water, it changes the ionic concentration, which compresses the double layer. A double layer is going to have a repulsive force. That is why particles are not going to attract each other. If the particles attract each other, mass develops, it will settle down. So, it is not happening there. So, what we do, we have added a coagulation. When the coagulant is added, it is going to compress the double layer. When the double layer is compressed, it weakens the repulsive force of the colloid. Understand? So then colloidal particles. Then this colloidal particle is going to attach to the electrolyte of the coagulant and falls down. So this is double layer gets compressed after addition of coagulant. Okay, this is one theory. Another theory is negatively charged particle are there, colloidal particles. When a coagulant is added like aluminum sulfate, add strongly absorbing species of opposite nature, Al3 plus, Al3 plus positive charges, and this electrolyte they are going to attach to the particle, negatively charged particle. So when the coagulant is added to the negatively charged particle, flux develops, many number of particles are going to attach, the mass develops and it is going to settle down. So second theory is charge neutralization. Another theory associated with theory of coagulation is called as bridging. It's called bridging. Here, adsorption and interparticle bridging takes place. What happens? Let's see. When a coagulant is added to the water, bridging occurs when a coagulant forms threads or fibers which attach to several colloids, capturing and binding them together. This happens. Inorganic primary coagulants and organic polyelectrolytes both have then capability of bridging. So higher molecular weights means longer molecules and more effective bridging, and they are going to settle down silly. And the fourth one is colloidal entrapment. What is this? It is sufficient amounts of coagulants like aluminum sulfate, perchloride, magnesium carbonate, and all can generate rapid precipitates, and colloids or colloidal particles may become enmeshed in these. It is going to enmeshed in these, and the settling takes place, which is called as colloidal entrapment. The colloids become enmeshed in the growing precipitate. Precipitates are there, and colloids are going to attach, and it is going to mix up with the precipitate and falls down or touches the bottom surface of the sedimentation tank. Now we shall see what are the coagulants or which are the chemicals which has got that character which binds the colloidal particles which are not easily removed in the sedimentation tank. Let us see. Lot of coagulants are there, commercially produced coagulants. There are some important coagulants. So we are going to touch some important coagulants that are generally used all over the world to treat water. The first one, very famous. Everybody is known this. Everybody know about this. It is called as aluminum sulfate. It's also called alum. Alum is the name given to aluminum sulfate with its chemical formula as Al2SO4 thrice 18H2O. So aluminum sulfate or alum both are the same. What will happen when the alum is added to the water? It reacts with bicarbonate alkalities which are generally present in the water to produce flocks of aluminum hydroxide. Aluminum hydroxide is formed which attracts the small particles and settles down to the bottom of the tank. The reaction is as well. See, when the alum is added to the water, it reacts with the bicarbonate alkalinity present in the water to form aluminum hydroxide, which is a precipitate, and this precipitate is going to attract very finer particles. So mass develops, it is going to settle down. So the equation says Al2SO4 thrice 18H2O plus 3A HCO3 bicarbonate gives you AlOH3 twice, that is aluminum hydroxide, calcium sulfite, 18H2O plus 6CO2. Carbon dioxide is evolved into the atmosphere. To produce the hydroxide flake, enough alkalinity should be present in the water. If the alkalinity is not enough, the CaHCO3, if the water does not have the sufficient alkalinity, we have to add the alkalinity in terms of lime or other sources. So under normal circumstances, dose of alum varies from 10 to 30 milligram per liter. So for every liter of water, at least you have to add 10 to 30 milligrams. So very simple. Add alum to the water. Add alum to the water. It has got all water naturally contain bicarbonates. So it forms aluminum hydroxide. This is the precipitate which attracts the particle and settles down. With that, we get another other chemicals also as a byproduct. So, if the natural alkalinity is not there, what we do, we add lime in the form of calcium hydroxide. So, it forms 2AlOH thrice plus 3ASO4, 3CaSO4 plus 18H2O. Sometimes sodium carbonate as soda ash is added to form alkalinity. See, it's not only the lime, we add soda also, and soda is added Al2SO4 thrice 18H2O plus soda 3Na2CO2 added. It also forms aluminum hydroxide. See here the formation of aluminum hydroxide is important. It is the one which is going to attract the smaller particles which are not going to settle down easily. So these equations you have to write in the examination when the question is asked about this. So what is the normal dose? It is 10 to 30 milligram per liter of water. Advantages. Advantages of alum is alum reduces taste and odor. It is cheap, easily available, and it is easily soluble in water. The disadvantage is it is going to form a huge sludge or the flog. So removal of that itself is the disposal of that sludge itself is very difficult, and taking the water out of the sludge is also a difficult thing. So this is one of the disadvantage of the alum. Another one is iron salt, which is ferrous sulfate, or it is also called as chlorinated copperas. This is also another coagulant which is used in the treatment of water or in the waterworks treatment units this is used. What is this copperas? Copperas is the name given to ferrous sulfate with its chemical formula as FeSO4 7H2O. When chlorine is added to a solution of copperas, the following reaction happens. When chlorine is added to the solution of copperas, you get this. The resultant combination of ferric sulfate and ferric chloride is known as chlorinated copperas. Chlorinated copperas is the resultant combination of ferric sulfate and ferric chloride and is valuable for removing color. Color is also because of very fine particles, very fine colloidal particles which are present in the water. And this is very helpful when the pH of the water is very low. It is quite effective in the pH range of 4 to 7 and above 9. So, resultant combination of ferric sulfate and ferric chloride is called chlorinated copperas. You get this when chlorine is added to the copperas. Copperas is nothing but ferrous sulfate. Here, this is the chemical reaction. See, in the examinations, you have to write down these chemical reactions and you have to explain it. So, without chemical reactions, if you will explain, you're not going to get the complete marks. So when FeSO4 is added to chlorine, it forms Fe2SO4 thrice, that is ferric sulfate, and FeCl3, which is ferric chloride, instantaneously, which is called as chlorinated copperas. And both of these are immediately available for the formation of ferric hydroxide. It is going to form ferric hydroxide. See, Fe2SO4 thrice, it reacts with calcium hydroxide. It may be present in the water, or when lime is added to the water, it forms calcium sulfate and ferric hydroxide. Ferric hydroxide is nothing but this is a precipitation. And if FeCl3, that is ferric chloride, which is present in the first step, and it mixes with calcium hydroxide to form calcium chloride and ferric hydroxide. So in both the reactions, ferric hydroxide is the one which is nothing but precipitate. It is going to attract the particles and settles down to the bottom of the tank. This is as far as ferrous sulfate or chlorinated copperas is concerned. Now we have ferrous sulfate. As you know, copperas is the name given to the ferrous sulfate with its chemical formula FeSO47H2O. When it is added to the raw water, it reacts with natural calcium carbonate alkalinity in water, but it's slow process. Hence, lime is added to the water. It is extensively used as a coagulant. Ferrous sulfate is extensively used as a see ferrous sulfate with lime is added, and if ferrous sulfate is mixed with chlorine, it forms chlorinated copperas as you studied in the second one. It is extensively used as coagulant for raw water that not colored. Ferric hydroxide is a gelatinous flock, which is heavier than flock formed by alum. See, this is an important. The flocks which are formed with the iron salts are more heavier. So it is heavier means it is easily going to settle down, and it functions effectively in the pH range of 8.5 and above. The fourth one or another one is magnesium carbonate and lime. See, magnesium carbonate is also a coagulant which is used to s- precipitate, or which is used to bring down the colloidal particles, or which is used to remove the colloidal particles in the sedimentation tank. What will happen when magnesium carbonate and lime are dissolved in or lime or dissolved magnesium hydroxide and calcium carbonate is prepared. See, this magnesium hydroxide is a precipitation. It is going to attract the finer particles, so it will fall down. If you remove MgOH twice, that means you are removing the colloidal particles from the water. Byproducts of above reaction forms a soluble sludge, so not commonly used. See, we have discussed alum. Alum is nothing but aluminum sulfate, and iron salts, copperas and chlorinated copperas, that is ferrous sulfate. Both have their advantages and disadvantages. As I said, alum is cheap, easy to handle, but its disadvantage is more sludge is formed. Iron salts are heavier salts, so they are going to settle down easily. Let's have a comparison. Let's see which salt is good and which condition that is good. See, if you compare alum and iron salts, iron salts form heavy flock as compared to alum. So iron salts flocks or the precipitation, the chemical reaction precipitation is heavier. If it is heavier means it is easily going to settle down and it will attract the other particles also. So more solids are going to remove easily. So first point is iron salts forms heavy flock as compared to alum. Hence more solids are removed. Second one, time of reaction and flock formation is less for iron salts. So reaction and flock formation is very less. It instantaneously forms. So time reduces. That's the advantage. So first advantage of iron salts is heavier flux, heavier weight. Second one is time taken for chemical reactions is very less. And it can be used over wider range of pH values. And it removes very fine particles which gives odor and which gives color to the water. So it removes taste also, it removes odor also. These are salts. And whereas in coming to the alum, less mud ball formation. Sorry, in case of iron salts, the mud ball formations because of the mud present in the water is very less as compared to the alum. If you use alum, you are going to get a lot of mud ball formation. Iron salts imports, that is a negative. Iron salts import corrosiveness. So alum is not going to import corrosiveness. That is the advantage. Whereas the iron salts imports corrosiveness, which is disadvantageous. So in that place, alum is good, and iron salts required more skills and control. Whereas alum does not need anything. 10 to 30 milligram per liter of alum, if it is added to it, that's enough. So iron salts are costlier. Alum is cheaper. So this way, iron and alum comparison can be made. These are the references being used. And this session is created by myself, Dr. Prashant, GC. So, thank you.